Okay, so last time we got into the first part of the complicated stuff, buffers, and we talked about buffers last time. Remember, a buffer is a solution that will resist changes in pH even when you add more acid or base to it. Really big fluctuations in the pH, as we talked about, and as you saw perhaps when you did the experiment the other day. The pH of the buffer will move a little bit when you add acid or base to it, but it should not jump really big in terms of pH unless it's a pretty bad buffer. A buffer does need to be made up of one of two combinations. So either a weak acid and the salt of its conjugate base, which is basically your Bronsted-Lowry definition of just 1H plus difference between those two things. Or it can be made up of a weak base and the salt of its conjugate acid. And remember, as we talked about, sort of how a buffer functions is it is necessary that both of those things are in solution to begin with. So really you can think of your buffer as having an acid part and a base part. And that's really what allows it to keep the pH from going crazy when you add additional acid or base to it, because it has both of those things in there. And that's why it has to be a weak acid or a weak base for it to be a buffer, and why you cannot have a buffer that's made up of a strong acid or strong base, because they are strong electrolytes which will 100% break apart in solution, and you will not be able to keep both the acid part and the base part of that buffer in solution. So again, that's why we have the weak one here. Buffers, as we talked about, are essentially common ion effect type situations, which means we can calculate the pH of these solutions by using the Henderson-Hasselbalch equation, which looks something like this. The pH is equal to pKa plus the log of the base over the acid, where the pKa is equal to minus the log of the Ka value. And as we talked about, for the most part, this is probably the one that you want to use when you're calculating the pH, as that's usually what you're asked for when you're dealing with buffers, which is what is the pH of the buffer. There is, again, the POH version of this, which I would probably not use, as we talked about last time, because again, you're usually interested in the pH anyway, so why not just go into that one? But the POH is equal to pKa plus the log of the acid over base, so it is different. pKb is minus the log of the Kb value. Thank you. The pKa plus the pKb, by the way, does equal 14. That's also a nice little conversion as well. So two things that we talked about. You can, if you recognize it as a buffer, which is really a common ion type situation, you could go right into the Henderson-Hasselbalch equation and calculate the pH of that solution or buffer. If you still wanted to do so and not use the Henderson-Hasselbalch equation, you could still use an ice table and just do an ice table calculation, and you should really get the same thing. The important part about doing the ice table calculation, as we've also talked about, is you need to make sure that you have an initial on both sides of the arrow here. So again, if it is a buffer, you should have numbers on both sides. Otherwise, again, you're not really doing a buffer problem. You're just doing a weak acid type problem. So if you want to do that, you can, but just make sure you have both sides, both parts of the buffer there initially. Now, the other thing that we talked about was really important as well. Whenever we do add volume to something, like if we do have a buffer and we add some volume to it, like some sodium hydroxide or like some, say, HCl, we do need to do this ice table in moles, as the moles will stay the same, but the molarity will change. So typically speaking, you need to do that first ice table in moles. After that first ice table, you can convert it back to molarity at the end of it using the total volume, and then you'll be in good shape. So whenever, again, we add sort of volume to something, the molarity changes, but the moles stay the same. So we always want to do that first one in moles. The other difference as well is, typically speaking, if you do have the moles in a calculation like this, there is no X's used a lot of times, because we already know what the change is. So like in your experiment, the change would be the HCl you added or the sodium hydroxide you added. So you actually just subtract the numbers, always the smaller numbers, so you don't get any negative numbers. And again, that would get you the right one. At the end of that sort of ice table, if you did add acid or base to your buffer, you once again have two options as to how to get to the pH. You should have a buffer still left over, which means you can't go directly back into the Henderson-Hasselbalch equation. Or if you want, again, you could lay up another ice table in lieu of the Henderson-Hasselbalch. Question on buffers, how they're made, what they do. No. All right. Then let us get to everybody's favorite thing, which is titrations. There it is. Yeah. So we're now going to talk about titrations and everything you wanted to know about titrations, but not really. But we're going to talk about what's going on here in this type of situation. So you should be familiar with titrations, and typically speaking, in a titration, we add one solution to the next. We use a burette to do so. We typically have one solution that we kind of know it's a known solution, like the molarity and stuff like that. And we oftentimes will add it to an unknown solution where maybe we don't know the molarity of it. And we will continue to add slowly through the burette. And we will add until we reach what is referred to as the equivalence point in the titration. And really, the equivalence point in the titration is in an acid-base titration, the point where the moles of the acid will equal the moles of the base. So that is essentially what the equivalence point means. You've added exactly the same number of moles of each of those things, and you reach the equivalence point. Now, sometimes people refer to the end point of the titration. And the end point of the titration is pretty much what it sounds like. It's where you lay up your titration and go, I'm done. Yes. And ideally, if you did a good titration, your end point and your equivalence point should be pretty close to one another. Otherwise, you didn't really do such a great titration in that case. We clearly all know that we usually will add an indicator, right, to our titration. And the indicator is used to allow us to visually see where we should perhaps stop the titration and where we should stop it to reach the equivalence point. So as you can see here, this guy right here has probably got our favorite one there, phenolphthalein. And phenolphthalein is a pH indicator. And as we talked about, it is colorless in acidic solutions, hence no color on the left there. It is also colorless in neutral solutions, but when it gets to basic solutions, it does turn a lovely shade of pink here. I would say nobody got that, but in my class, they usually do get that light color of pink. And it usually happens right when I say extra and credit. All of a sudden, everybody knows how to titrate. Before that, nobody could get a light pink in the building. But you say those magic two words during titration. Everybody's got light pink. Everybody's shoving flask in my face. Does that look light enough for extra credit? So that is typically where you want to stop. And when we do use an indicator, as we've talked about, and we'll talk a little bit more about a little later on this chapter, indicators do work over a pH range. And again, something like phenolphthalein works on a pH range of 8.3 to about 10. And it's about colorless in this range here. And again, it gets gradually pink, pink, super pink there towards the back end there of the pH scale of the 10. So ideally, when you choose an indicator for a titration, it's really important to have an idea as to where your equivalence point would be in terms of pH. Because clearly, if I were going to use phenolphthalein for a titration where the equivalence point's at a pH of 4, that's not going to do me much good because my solution is just going to be colorless all the way through my equivalence point, right? So as we'll talk about, you really do want to choose an indicator that will change color near the equivalence point. Clearly extra credit word right there, right? Spell phenolphthalein. I'm not even sure I spelled it right, so you spell it right. And I hope you our bonus word there on the next exam, I imagine. Just write it anywhere. Anywhere you feel you could fit phenolphthalein nicely into an answer, just put it in there. So when we do a titration, there's a few different types of titrations we're going to talk about. And as I mentioned earlier, we will answer the question, are the sentence that you always hear when people do titrations, which is, I just added 1 drop and it went super pink. So we'll explain really why that happens again, as we go through this. So let's take a look here at the first type of titration we're going to look at, which is a titration of a strong acid with a strong base. So we'll do a little hydrochloric acid and a little sodium hydroxide. And that's going to do a little reaction there and give me some water. And a little sodium chloride action happening. So for orientation purposes here, the setup is in the burette. We have the sodium hydroxide. And in the beaker or the flask, we have the HCl. So we're adding the sodium hydroxide in this case to the HCl. And this is a titration curve here, and titration curves pH versus volume of sodium hydroxide added. And this is a typical sort of S curve that we see going on here. And obviously, since that's the very beginning here, we only have an acid. We're starting at a low pH. And as we add our sodium hydroxide, we will see obviously a rise in the pH there until it sort of levels out there up on top. So as we talked about with buffers, when we do calculations involving titrations, we are clearly doing nothing but continuously adding volume to volume, which means as we do calculations, typically for titrations, and we have to perhaps do an ice table, we definitely want to do it in moles, just like, kind of did with the buffers in this situation. So there's really in most titration curves 4 distinct parts to the titration curve. We have sort of at the very beginning here, part number 1. We have after we add the first drop to before the equivalence point. That's like the second part of the titration curve. We have right there at the equivalence point is the third type. And I'm sure you all stopped at the equivalence point, but just in case you didn't, and that pink color didn't stop you, and you just keep going past the equivalence point would be sort of the 4th part of the titration curve. So we're going to talk about what is happening at each of these parts of the titration curve. It's really important as you go start to do problems, as we'll talk about some different types of titrations, that you first perhaps identify what type of titration you're dealing with. And secondly, it's really good idea to have an understanding of like where you're at in the titration curve. So a lot of times if you have an idea as to sort of where you're at in the titration curve, before you even do the calculation, you should actually know what type of calculation you should be doing, which kind of makes it easier than trying to figure out what you should do if you kind of know what you're supposed to do as you go into it. So we're going to look at this one here. So why not just start right there with number 1? So the very first part of this titration curve here is before we add any base. So the only thing I got going on in my beaker at this point in my example is a little HCl, yes? So that means, how would I find the pH of a strong acid? That is not the true question. What do you think? So it's a strong acid. Will it stay together or break apart? Yes, it will break apart, I think is what you're answering. Yes, so it will completely break apart, right? So because it's a strong acid, right, we know that 100% of it will break apart into H plus and Cl minus. And really the important thing here for pH is the H plus concentration. And since I know the molarity of this guy, I could very easily figure out the molarity of the H plus concentration, which means I could go into my pH. So at the very start of this type of titration, because the only thing that we have in our flask, in our beaker, is a strong acid, and because a strong acid will completely dissociate in solution, all we have to do is basically take that as our H plus concentration, and you could go right into the pH equation and actually get the pH of that solution. Questions on that one there? So that part not too bad. All right, so you got your whole setup here. You got your titration all set up. You got your beaker under there, and you figure, well, maybe I should start titrating. So we're now going to talk about what happens here in the second part of the titration curve. So this is the part where you've added your very first drop of sodium hydroxide to right before you hit that equivalence point, which is over here. So anywhere in this sort of region, we are adding sodium hydroxide, which means once I add sodium hydroxide, I am going to get a chemical reaction that's going to occur right between the hydrochloric acid and the sodium hydroxide, which means I will need to do an ice table. And that ice table, as we just talked about, should be done in moles. So we would have to do an ice table here in moles. So at the second part here, we have added some sodium hydroxide. We are before the equivalence point. And that means that we wanted to figure out the pH. We will do our reaction of sodium hydroxide plus my HCl. Again, going to give me a little bit of water and a little sodium chloride action happening. So in this particular case, again, just for reference sake here, we are adding our sodium hydroxide, and we are starting with, right, basically our HCl there in the beaker. So let me be clear here about what I'm about to say. Write it down. I am making these numbers up. All right, so I'm just going to randomly make up some numbers. People always ask, like, where did these numbers come from? All right, so I'm just going to make up some nice, easy numbers to follow along with in terms of what's going on. All right, so initially, I'm going to say I am starting with 4 moles of HCl. And once again, we do need to do this table in moles because we're adding sodium hydroxide to it. Now, if I am before the equivalence point, should the moles of sodium hydroxide that I am adding be less than, equal to, or more than the moles of the HCl I'm starting with? It should be less than, right? And that's because we know if we're at the equivalence point, they're going to be equal. So if we're at the equivalence point and they're equal and we're not there yet, they are not equal, and what we're adding is less. So I'm just going to make up a number of 2 moles here, which is definitely less than where we are at there at the equivalence point. Now, when we get to the change here, very much like what we did with buffers, we should know the change. And the change is basically at this point, the sodium hydroxide is our limiting reagent, it's the smaller guy. And the HCl is our excess reagent, the larger guy. And that means that the change here should be the moles of sodium hydroxide. By the way, if I selected 4 as my change, I'm going to get a negative number for the first guy, and that's not good. So always pick the small guy. I think I lectured you on always picking the small guy, even though your head will say, don't pick the small guy. Pick the small guy. And at this point, we will reach equilibrium. I'll have none of my sodium hydroxide. I got me 2 moles of this guy and 2 moles of this guy here. At this point, you should, like we did with buffers, convert this back to molarity. And the total volume at this point would be how much of the HCl we started with and how much sodium hydroxide we added. So you would want to convert this back using the total volume to get to molarity. And again, you really want to do this because it will always sort of put you in the correct units that you need. Now, if you're not sure what to do at this point, you can also look at the ice table, and it oftentimes can give you maybe some ideas as to what is going on. At this point, I have sodium chloride and HCl, by the way. Is that a buffer? No. It's because I paused a while. Is that why you changed your mind? I imagine that's probably why you did that. It is not, because HCl is what type of acid? It's a strong acid. You can't have a buffer that's a strong acid, right? So this is not a buffer, and this is like, I'm going to screw this calculation up because I have 2 numbers and I have the Henderson-Hasselbalch equation in my head, I'm just going to use it. And this is very, very common mistake that people do that. They get see two numbers, they roll right into that Henderson-Hasselbalch equation. So this is not a buffer, even though they are related to each other because it is a strong acid. So we want to think about the two things we have left. This is a salt, right? What type of salt is that? Is it an acidic, neutral, basic? It is a neutral salt, right? Because it's a group 1 and it comes from HCl, right? So not going to do any type of hydrolysis, which means, frankly, who cares? That means really the only thing we're left with at this point is still HCl, which is a strong acid. So we really need to do this ice table only to figure out what the new molarity of our HCl is at this point in the titration. And once we have that, we pretty much have the H plus concentration because that's a strong acid. And it's right back into our pH equation at this point. Any questions on that? So as you're doing this type of titration, as soon as you add that very first drop of sodium hydroxide or whatever base you're adding, all the way through, you want to stop anywhere through until you reach the equivalence point. You need to do at least one ice table. That ice table should be done in moles, and really the entire purpose of that ice table is to figure out how the concentration of your strong acid has changed. And once you figured out the new concentration of your strong acid, you could go right into the pH equation basically to figure it out. Any questions on that there? Okay. So we are chugging along here in our titration. We're happy. We're talking to people next to us. And we're approaching the equivalence point. And as we approach the equivalence point here, we are going pretty vertical. Yeah, there's a pretty vertical jump there in the equivalence point, to the equivalence point, really. I'll make it orange. And by the way, after the equivalence point, there's also a very big jump in pH as well. And that is going to take us to the equivalence point. And this is also the reason why people oftentimes say that saying of, I only added one drop and my thing went from like no color to like super dark pink. And that is because when you think again about something like phenolphthalein, which on the 8.3 scale is kind of colorless, but down closer to 10, it's pink, right? So if you're titrating, and you add one drop, as I go from here to here, is there a big difference in the volume? There's not. It's basically a straight line. But is there a big difference in the pH? There's a very big difference in the pH. So if you missed it by a drop, you could find yourself up here, right? And if you do find yourself up here, and blink the screen, I'll take it back there. You can find yourself up here, and your indicator, right, is going to be super dark pink, right? Because it's like a pH of 10. Are you very far off your volume at your equivalence point? No. So if you had a mean teacher, I don't want to say mean teacher, but if you had a teacher that yelled at you and said, oh, that's too pink, go do it again. Anyone? No, he did not. All good teachers, I suppose. You would not really have to be too worried about it if you were really careful, right? As you went to the equivalence point, you only missed it by a drop or so. It's not going to make a very big difference in your calculation in terms of the volume. The reason sometimes teachers will tell you that looks too dark pink, you should do it again, because if I ever way over here, color of my solution is going to be the same dark pink, right? And now I'm pretty far away from my equivalence point volume, which is way over here, right? That's my equivalence point volume. So that's why oftentimes they'll tell you maybe you should do it again because it's really dark pink. They don't know how careful you were. But if you were doing a really good titration and it was like colorless and it's pink, not colorless, and it goes back, and then you just added a drop and it went kind of from colorless to pink, you're probably right there in terms of the volume where you need to be, even though your indicator went really, really pink. But again, if you weren't careful, like when I used to titrate, just open that baby up, shut it off, and go, cool, dark pink. That's fairly close to the equivalence point. It's not that far off of it. All right, I was always the first one done. I didn't understand that light pink thing. I didn't understand it. So That is, again, the reason why we will see sometimes the indicator jump really, really pink. All right, but now that takes us to the equivalence point here, and let's talk about what happens when we actually do reach the equivalence point. And when we reach the equivalence point here, which is our third sort of position, the equivalence point, we are obviously still adding sodium hydroxide to our HCl, so we will get our reaction that will occur. And once again, we are starting with this guy, and we're adding this guy here. So again, we are going to do an ice table here. And once again, it does need to be done in moles because we are adding. And again, I'm going to start with my 4 moles of HCl, which means if I'm at the equivalence point, how many moles of sodium hydroxide should I have? Equivalence point means that you have equal amounts, right? So you should have 4 moles of sodium hydroxide as well, and nothing there. The good news is at the equivalence point, since they're both the same number, you can't choose the wrong number. Ideally, I'll say maybe you can't choose the wrong number. The number here should be 4, should be your change, since that's the only number we got going on. And that would be 4 all the way across. And that means none of that and none of that, which is basically the definition of the equivalence point, where you have equal moles of each of those. We got 4 moles of this guy. We once again could convert it back to molarity by dividing by the total volume. So again, if we take a peek at our ice table, really the only thing standing at this point is the sodium hydroxide. Now is the sodium chloride, which is like hydroxide without the hydroxide part of it. It is the sodium chloride here. And that, again, as you just told me a second ago, is what type of salt? It is a neutral salt, which means, frankly, you don't even need an ice table at this point in the titration. The pH should always be 7. That is why they call this type of reaction an acid-base neutralization reaction, right? You basically just make water at this point is what you're making, and the pH ideally should be 7. So if you are doing a titration of a strong acid and strong base, no matter what combination of strong acid, strong base, and you reach the equivalence point, you should hit a pH of 7 when you're there at the equivalence point. And because you should pretty much only have a neutral salt left over at that point, along with water. Any questions on that there? All right, so back to our curve here. We hit our equivalence point, and we see that jump in pH. And we see that jump in pH because, frankly, the indicator didn't stop you. And now all you're doing at this point is dumping more sodium hydroxide in, right? So if you think about sort of the ice table we just did there, at this point, you're just adding more hydroxide, right? All that HCl is going to be gone at this point, and you're just littering it with hydroxide, which means the hydroxide concentration goes up, pH will go up, the H plus concentration will go down in this case. So at the 4th part, past the equivalence point, that again is why we see that kind of big jump right after the equivalence point, because you just influx your solution with a bunch of hydroxide. We're going to go after the equivalence point here. We still have a reaction happening here of HCl plus some sodium hydroxide. Gives us some water and some sodium chloride. And once again, we are starting with this guy and we are adding this guy. So initially here, I got my 4 moles of HCl that we've started with in all of our titration parts here. Now, since I am after the equivalence point, should the moles of sodium hydroxide be less than, equal to, or more than 4 in this case? Should be more, right? Because again, at the equivalence point, they're equal. In this case, we're now going to add just a bunch more hydroxide. So I'm going to make up the good number of 6. Seems like a nice number. And we go 0. Now, something does change here after the equivalence point. The limiting reagent in this case is which one? It is the HCl, right? We have less moles of it. So that's got to be your change. So again, don't take the bigger number. So this is going to be -4 plus 4 in this case. This is going to get us 0, 2 moles, and 4 moles. Once again, we can convert these things back into molarity by dividing by the total volume. Once again, you should also look at your ice table because it can sort of help you hopefully figure out what's going on. First off, are these two things related to each other, sodium hydroxide and sodium chloride? They are not a buffer. They are not related to each other. Again, just because you have two numbers, don't use the buffer equation. This, again, as we've been talking about, is a neutral salt, so we're not even going to really worry about that, which means at really this point in the titration, as I've been talking about, you're just dumping in some sodium hydroxide, which is a strong base at this point. And because it's a strong base, it also, like our strong acid, will completely break apart into sodium ions and hydroxide ions. And now that I know the molarity of it, the thing that's important here is the hydroxide concentration, which would be probably the same molarity in most cases. And because I now have the concentration of OH minus, do I calculate the pH directly at this point? If I have OH minus, do I get the pH from that? I got to first get what? Yeah, the POH first, yeah? So you got to remember that is the hydroxide here, not the H plus. So you got to get the POH, and then you could get yourself to the pH by really subtracting 14 would probably be the easiest move there, which would be 14 minus the POH, yeah? So when you are past the equivalence point in this type of titration, you need to do at least one ice table. It does need to be done in moles. And the purpose really of this ice table is to figure out how much strong base you dumped into your solution at this point. Once you have that, you will have the hydroxide concentration. It'll get you to the POH and then get you to the pH for happy parts of the titration curve. Yes. Also a little slightly different about what's going on. And let me be really clear, what we are talking about here in these 4 spots are specific to this type of titration only, a strong acid and a strong base. We'll talk about some others in just a second. They're a little bit different. Any questions on that there? All right, so let's just try one for fun. Let's do, let's see. What is the pH after 23.5 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar HCl in a titration? All right, take a moment and do it. I'll do it as well. Hopefully we'll get the same answer. So this titration is set up the same way we just were talking. We're adding the sodium hydroxide to the HCl in this case. Okay, so let's take a look, see how you're doing. So obviously we're doing titration here. We were obviously added some sodium hydroxide in this case. So we definitely know we should do an ice table. We also know we need to do it in moles, right? Because we're adding volume. So we might as well get the moles of everybody to start with. So if we want our moles of sodium hydroxide, we do need to change our volume into liters. So divide it by 1,000 or move your decimal place over a few places there. We'll do that for you. We're going to times it by the molarity here of our sodium hydroxide. Liters are going to cancel, and that's going to get us 0.023 times 0.1. 0.00235 moles of sodium hydroxide. We're going to do the same thing here for our HCl. In this case, we have 25 milliliters, so divide it by 1,000. We'll also times it by the molarity of our HCl. Going to get us 0.0025 moles of HCl. So again, this is what we're starting with, and this is what we're adding. And that means we do need to have our equation that's going on. So we'll do a little sodium hydroxide plus some HCl. A little double displacement action happening here, right? Positive, negative, guys. Going to give us some water and some sodium chloride in this case. So initially here, we got 0.00235 moles of sodium hydroxide. That's 0.0025 moles of the HCl and nothing going here. So the first question is, am I before, am I at, or am I past the equivalence point? I am before, and sometimes people overlook the usefulness of your ice table. I know, again, I am adding this guy, and I am starting with this guy. So the moles that I am adding are less than the moles I'm starting with, which means I am before the equivalence point. So these are good things to sort of know, kind of where you are at in the titration. That means that I know that all my sodium hydroxide I'm adding is really my limiting reagent, as it is the smaller number as well, and it should all get used up in this case. So the change here is going to be our sodium hydroxide because we are before the equivalence point. Be plus 0.00235 moles. That means when we reach equilibrium, as we would expect here, all of our sodium hydroxide will be gone. We will have 0.00015 moles of our HCl. We'll have 0.00235 moles of our sodium hydroxide. At this point, you should really just get into a habit of converting it back to molarity. So we're going to go with a total volume at this point of, we started with 25 milliliters. We added 23.5 milliliters, giving us 48.5 milliliters as our total volume at this point in the titration. We want to convert that back into liters. Divided by 1,000 gets us 0.0485 liters on each side, right? That's going to get me here 0.00309 molar, and 0.0485 molar. Any questions so far? Once again, if you're not sure what you should do at this point, don't overlook the ice table that you made. So we could clearly see we have sodium chloride and HCl left over at this point. And as we talked about, the sodium chloride is still a neutral salt, right? Which means it's not going to really do much for us. That means that really the thing that we have left over here is still our strong acid. And this is where knowing that you're before the equivalence point comes in handy, because you should know that is exactly what you should end up with, right? We're doing this ice table to figure out how much of our acid is left over, basically, at this point. So because of that, that is going to equal our H plus concentration, which means we are good to go right into our pH is equal to the log of the H plus minus the log 0.0309. And that's going to get us here, we'll call it a 2.51 pH at this point in the titration. RAZ, 2.51. Any questions on that there? To see how we did here, let's see. I think this was this titration. 23.5 is right there between those two numbers, and 2.5 falls right between. Not bad. I don't have to quit yet. That's good. Any questions on that there? All right, so this is a strong acid, strong base titration. Those are the 4 points along the titration curve. You do need to be able to calculate any part of that titration curve, any point that I choose, all like 200 points if I'm really upset with you at that day. But you should be able to calculate any point along the way. By the way, when we do titration problems, just so you know, and you come across problems perhaps in book or wherever it may be, and there's like multiple parts to it, like part A, what's the pH after you add 20 milliliters, or part B, what's the pH after you add 60 milliliters. They're not additive typically in titration problems. So part A is like a whole separate problem. You just open it up to 20 milliliters. Part B, you start at 0, open it up to 60. So don't add those volumes together in a problem or anything like that. So they are typically just kind of individual problems, even though they're all kind of together sometimes. All right, then looky there, we have the same one. Let's look at a different one maybe. There we go. All right, the next type of titration we're going to talk about is a titration between a weak acid and a strong base. So this is a different type of titration. It is going to be set up the same way. We're going to have up in our burette, in this case, the sodium hydroxide. Down there in the beaker slash flask, we're going to have our acetic acid in this case, which is a weak acid. So we are adding, again, the sodium hydroxide to our acid in this case. We see a titration curve that looks very similar to the first one, this sort of S curve that happens. And we can see a rise in the pH. So we're starting at an acidic pH, and we do see a rise in the pH. We also see the same thing that we saw in the first one, a kind of vertical leap there to the equivalence point, and then another vertical leap after the equivalence point, and then we kind of finish up there with the rest of the titration curve. Now this curve, just like the last one, has the exact same 4 important locations along the way. And we're going to talk about what's happening at each of these locations. So once again, the first location is before we even start the titration. So just with the acid sitting there. The next part is the same part after we add the first drop to before the equivalence point. Third part is the equivalence point. And the fourth part is after the equivalence point. So these are the 4 parts of this titration curve here. And let's talk a little bit about what's going on at step number 1 here. So at step number 1, we are before we add any base. So before we add base, that means once again, in this case, the only thing I have sitting here in my beaker is my acetic acid, which, as we just talked about, is what type of acid? A weak acid. How do I find the pH of a weak acid? Do I just go right into the pH equation? No. It's a weak acid, which means ice table time. Yeah. So this is basically a Ka problem like we did in the previous chapter. You're going to set up an ice table. So we're going to take something like our acetic acid. It's going to break apart into H plus and a little bit of acetate here. We are going to initially do this table actually in molarity because we haven't added anything at this point. So all we got sitting there is our weak acid. So this is going to be a molarity table. These are going to be zeros and our x's, minus x, plus x, plus x, equilibrium, initial concentration, minus x, x and x. This goes into our Ka expression, which is our products over our reactants. And it equals Ka value of 1.8 times 10 to the minus 5, perhaps, for acetic acid. So just like normal, we would take our equilibrium, go into here. We would solve for x. Now you could solve for x all the ways we've solved for x before. You could quadratic it. You could make an assumption if it works. Whatever you like to do on that. A lot of times the assumption will probably work, so you might want to try that. But if not, again, you could quadratic it. And the important part here is once we solve for x, the x value here is going to equal our H plus concentration. So that's going to equal our H plus concentration, which means then we can calculate the pH by going into the pH formula there at that point. So at this type of titration, when we're dealing with a weak acid and a strong base, is quite different than the first titration here. We've got a little bit more work. The good news is it's something you've done before. It's just a Ka type problem, and you want to solve for X, and that will get you your H plus concentration. Any questions on that there? So again, you can see this titration a little bit different than the last one. So now we're ready to actually start our titration here. So we're going to start to add some sodium hydroxide to this acetic acid. And that will put us on the titration curve, moving towards the equivalence point. Very good. Yeah. So we're going to look at number 2 here. Again, starting our titration here and moving ourselves towards the equivalence point. And let's talk about what happens in this case. So in the second part of the titration curve, we are before the equivalence point. And in this case, we are going to get a reaction that's going to occur. So we're going to get a reaction between our acetic acid, in this example, and our sodium hydroxide. A little acid-base reaction happening here. And that's going to give us a sodium acetate and some water, right? Pretty much a double displacement reaction happening here, right? So once again, for purpose sake here, we are starting with our acetic acid. We are adding our sodium hydroxide. So we're going to need to do an ice table at this point. Should this ice table be done in molarity or moles? Be done in moles because we're adding volume, right? So again, I'm just going to make up the number here for my acetic acid, which is 4 moles. And because I am before the equivalence point, should the moles of sodium hydroxide be less than, equal to, or more than 4? If I'm before the equivalence point, they should be less than. So I'm going to make up a number of 2 moles in this case, and 0 here. This means that at this point, it is the sodium hydroxide that is the limiting reagent, which means this will be -2, -2, and +2 moles. That means that when I reach equilibrium, I got 2 moles, 0, and 2 moles of this guy right here. Any questions so far? All right, so just like we did in the previous one, we're going to throw this back into molarity at this point. We want to divide by the total volume, which again, in this case, would be how much acid you started with and how much base you added. So we'll turn this into molarity, turn this into molarity. And we are still looking for the pH at this point. So again, your ice table is really important here. We can look at it and we see we have sodium acetate left over and acetic acid left over. Are those things related to each other? Acetate and acetic acid, they are related to each other, right? They are what? They are a buffer, yeah? That is a weak acid and the salt of its conjugate base, your classic definition of a buffer. And because this is a buffer, that means if I want the pH at this point, one way would be probably the easiest way, go right on into your Henderson-Hasselbalch equation at this point. Your alternative to that is not to do the Henderson-Hasselbalch, and you could do a second ice table if you wanted to with acetic acid. And again, this would be a situation where you got to make sure you got numbers on both sides. Probably, again, the Henderson-Hasselbalch would be easier. So obviously, much different than the first titration here before the equivalence point. The good news is every time you have this type of titration, you need to do at least one ice table, and you will always hit yourself a buffer. You also hit yourself an acidic buffer at this point. And you're basically doing the ice table to figure out the concentration of your buffer components, basically. And it's your call at that point. You could go into the Henderson-Hasselbalch, or again, if you don't want to do the Henderson-Hasselbalch, you can do a second ice table. So as we look here at our titration curve, we are starting a little bit higher in pH to begin with because we have a weaker acid. we have a little less of a steep climb here because we are buffering all the way through here. As we talked about, right, there is a limit to buffers. What happens when you get to the end of the buffer? You get a really big jump in pH, and that is what happens to the equivalence point, because right about there, you broke your buffer, basically, that you made. So you actually broke the buffer, and now you're just adding more sodium hydroxide, which is why you will see that big leap to the equivalence point in this type of titration. And you'll see sort of a mild sort of change in the pH as you're going up, but eventually you'll add enough sodium hydroxide that it'll actually go through the buffer you made, and you'll see that big jump to the equivalence point. This is also a demonstration of something that we talked a little bit about when we were talking about buffers. Now, we talked about the idea that you cannot have a buffer that is made up of a strong acid or strong base, but you could definitely make a buffer from a reaction of a weak acid with a strong base. And what is the buffer part is the end part. The strong base is gone at that point. So this is what sometimes is referred to as making the buffer in the solution. So you actually make a buffer by taking a weak acid and strong base, but the strong base gets completely used up, and what you're left with at the end is a buffer. Any questions on that there? All right, so far, two different spots, two same spots, but two different types of calculations in this type of titration curve. So let's talk about what happens when we reach the equivalence point in this type of titration. So we're going to be right here at the equivalence point in step number 3. And let's take a look at the third part, which is at the equivalence point. So obviously, if we are at the equivalence point, we are still going to have our reaction, and in this case, a little acetic acid plus some sodium hydroxide. Again, going to make yourself a little bit of sodium acetate and some water. Sounds good. And once again, this is what I'm starting with, and this is what I'm adding. So we will once again do this ice table here in moles. And I'm going to start with my made up number 4 moles again. Now, since I did reach the equivalence point here, the moles of sodium hydroxide should be 4 as well. Yeah, so it should be equal. Now, by the way, if you are not given like the volume to reach the equivalence point, say in this titration, how can you figure out the volume to reach the equivalence point? If you're not sure. Well, you can do, if it's a 1-to-1 relationship, you can use M1V1 equals M2V2, and M1V1 would be your acid, and M2V2 would be your base information. If it is a 1-to-1 relationship between those guys, and it has the same molarity, you need the exact same volume to reach the equivalence point. So there are a few different ways you could also figure it out as well, which is, at this point, I probably know the molarity of the sodium hydroxide. And if I didn't know anything else, I know it should be equal moles. So I know the molarity and the moles, which means I could just use the definition of molarity and figure out the volume that I would need to reach the equivalence point. So there's a few different ways that you can figure out the volume to reach the equivalence point. There will be problems you'll come across where they will not tell you the volume to get to the equivalence point. They'll just ask you what is the pH at the equivalence point. So stoichiometry move, M1V1 equals M2V2, just a definition of molarity, and understanding you should have the same number of moles of your acid. These are all the ways you could kind of figure out the volume. The reason we need to figure out the volume is, after this ice table, we need to convert it back to molarity, which means we need to know how much volume of sodium hydroxide, for example, we added. So sometimes that is the reason you really need it, is at the end of this table. All right, any questions on that? Clearly here we got 0 of our sodium acetate. Once again, since it is the equivalence point, we can't pick hopefully the wrong number. It should be 4 in this case. And that's going to be 0. That's going to be 0. That's going to be 4. And once again, this is where knowing the total volume is going to be important because we do need to convert it back to molarity at this point. By the way, why am I not putting anything in by water? Yeah, it's not going to really do anything anyway. So why put extra numbers that you might want to use wrongly, right? So we're just leaving it off. All right, so we did this ice table. We're at the equivalence point. Once again, we could look at our ice table here, and we see we have water left over, and I have sodium acetate. Sodium acetate is a salt, right? And when we have salt and water near each other, what is the possibility that could happen? A little hydrolysis reaction, right? We could have a salt that will react with water. Will this salt react with water? This salt is sodium acetate, right? Which basically will break apart into sodium ion and an acetate ion. We'll start with the sodium. Will that go through hydrolysis? It will not because it's group 1, right? So they're neutral. How about acetate? Where did that come from? Of what? Is the conjugate base of acetic acid, yes? And acetic acid is what type of acid again? Is a weak acid, which means this is this conjugate base. Will it go through hydrolysis? I feel like it got quiet, and I feel like a nod in the front row. So I'm going to go with the nod in the front row. You are correct. Yes, it will go through hydrolysis because remember, anything that comes from a weak acid or weak base is relatively strong and will react with water. So lo and behold, second ice table action happening right about now. So because we have this salt that will go through hydrolysis, and heck, we have water there as well, they're going to react with each other. And we will need to do a second ice table because one is just not enough in this case. Yeah. So we're going to react this with some water. The good news is we know it comes from an acid, which means, as you correctly said there, that's going to be a base. And a base does what? Donate or accept? Accept an H+. The H+ is going to come this way. When we react in a hydrolysis reaction, we always make where it came from, which is acetic acid. And I'm going to produce a little bit of hydroxide in this action right here. This hydroxide is something we've seen before. That means that without doing the calculation, acidic, basic, or neutral, this solution going to be basic because we're producing hydroxide. We're going to do an ice table at this point, and this is why it does need to be in molarity, because if you don't have it in molarity and you go into this ice table, you will end up probably with the wrong answer. So again, just flop it back to molarity. This kind of equilibrium guy here is going to become my initial here. So this guy is going to go right on into there. This is going to be a table with x's. Minus x plus x plus x, which means initial minus x, x, and x. This is going to go into my K expression, which will be my products over my reactants. By the way, this is a K, A, B, C, D, F, G. K, B action, right? That is the other thing people screw up on still at this point. Yeah, so you need a KB. Probably in the titration information, you will have your Ka given to you. So that is where our Ka times Kb equals Kw comes into play. So our Ka times Kb equals Kw. So we flip it around and get the Kb. Obviously, at this point, we would do like normal. We're going to solve for x. X in this case, though, equals the hydroxide concentration, which means we then could get to the PaOH and then to the pH. Yeah. So a little more difficult here at the equivalence point in this titration. You can't just say 7. And here you need to actually do a minimum of 2 ice tables. The first ice table is just simply to figure out what is the concentration of your salt. The second ice table is a hydrolysis problem. And that will get you where you have to kind of flip it around to the right K value that you have. So in this type of titration, when you're titrating a weak acid with a strong base, when you reach the equivalence point, it will always be basic pretty much because you are producing a salt that will go through hydrolysis and producing hydroxide. This is why we use phenolphthalein in like our vinegar titration with this, because the equivalence point's like 8 point something. And that is why they tell you to get it to the lightest color of pink, that you barely can see the pink, because 8.3 is where that phenolphthalein is colorless. And that's why it's like you got to hold it up to see the light pink. That will put you close to the equivalence point. Yes, sir. Yeah. Yeah. Yeah, so they would be the equilibrium here. So if you were going to table this one up, you probably would want to do your just like kind of like a Ka problem with the acetic acid. And we would use kind of like we were just doing here on this last one. These equilibrium guys would become your initials down here. And again, that's the important part is you would need a number here and here to make sure your algerine as a buffer. Yeah. Mhm. Other questions? All right. Well, that looks fun. Let's talk about what happens when we go past the equivalence point, because I've seen your titrations and sometimes that pink does not stop you and you go, let's just add more. So now we're going to jump past the equivalence point where again, you're basically just dumping in some sodium hydroxide. We're going to see it really peak out here. So let's talk about what happens here in the fourth part, which is after the equivalence point and this type of titration. So we are going to have our same reaction, so that we're doing acetic acid here and some sodium hydroxide. Again, we're going to get the same reaction occurring, a little sodium acetate and some water here. So once again, we are starting with this guy. We are adding this guy. So we are going to do an ice table here again in moles. So I'm going to start with my magical 4 moles here. Now we know that we are past the equivalence point. So you're going to correctly tell me that the moles of the sodium hydroxide should be more right at this point, right? So we'll go with 6 and 0. Again, we get the same sort of switch that occurs at this point in the titration because you're dumping way more sodium hydroxide. You have an excess amount of sodium hydroxide. The acid actually becomes the limiting reagent, and that is going to be our change at this point. 2 moles of this guy, 4 moles of this guy. Now, like normal, we're going to convert these guys back into molarity using, again, the total volume at this point in the titration. So again, just, you have this ice table, you have the reaction. How, like, a look at it to help you decide. First off, buffer or no buffer here? No buffer. Yes. So again, just because you have 2 numbers, do not use the Henderson-Hausbach, only specifically for a buffer situation. We have 2 things happening here. We have a salt that we just talked about at the equivalence point that will go through hydrolysis and will produce OH minus as a conjugate base. We have sodium hydroxide, which is a strong base. Out of the 2, the sodium hydroxide, which is a strong base, or the sodium acetate, which is a conjugate base that will go through hydrolysis, which one is stronger? It is the sodium hydroxide, because all the sodium hydroxide has to do is go for a swim, and it's going to produce hydroxide as soon as it goes into that solution, right? The acetate's got to go find some water, do a little reaction, a kind of weak acid type thing, weak base and electrolyte. So what we typically do at this point in the titration is, because the sodium hydroxide is going to be really the major contributor to the hydroxide in that solution, we ignore the contribution from the salt. because this is going to be much, much stronger of a base. So what that means is essentially at this point in the titration, we know the concentration of OH minus, which means we could get to the POH and then get to the pH. So in this type of titration, as you pass the equivalence point, you need to do at least one ice table in moles. The purpose of this ice table is to figure out the concentration of your strong base you got left over, and then you could go into the POH and then to the pH equation. Yeah. So we won't be covering that type of titration. There's a lot going on in that because you got two weak guys. So like, for example, when you get to like the equivalence point, you probably got both parts going through hydrolysis, and you got to do like the Ka versus the Kb and stuff like that. So we're not going to really cover that type of titration. So it would be a little bit different depending on sort of what you're adding. Other questions? All right, so this is a weak acid, strong base titration. The good news, if there is good news, is you actually know how to do all these problems at this point. The key thing that people screw up on is not understanding what type of problem you should be doing. So as we just talked about at the very beginning, it is essentially a Ka weak acid problem, no matter what you got going on. And the second part is basically a buffer problem that requires at least one ice table and the Henderson-Hasselbalch equation. At part 3 here, at the equivalence point, it's a hydrolysis problem, which requires two ice tables. And basically, after the equivalence point, it's a strong base problem. So this is what I was saying earlier. If you understand the type of titration you're doing, like this titration, and you understand where you are in the titration, you should actually know what type of calculation you should be doing before you even pick up the pencil, which will make the calculation hopefully a lot easier to do, rather than what a lot of people don't take a second to think about it. They jump right into the calculation and try to figure out what's going on, where numbers are flying around in their head and on their paper and not really sure what's going on. So when you're doing titrations, it's really important to just take a moment and figure out where you are in the titration curve. And you really should know what type of calculation you're doing. Even like the first one, if I know I'm at the very beginning of the first one before I add anything, it's a strong acid. If I'm before the equivalence point in the first one, I know I need to do an ice table to figure out my strong acid concentration. Still a strong acid problem. If I'm at the equivalence point in the first type of titration we did, I know it's a pH of 7. I don't have to do much. And if I'm past the equivalence point in the first type of titration we did, I know it's going to be a strong base problem, so I need an ice table to figure out my strong base. Same thing here. If I know I'm before the equivalence point, I should hit myself a buffered problem at some point. If I'm at the equivalence point, I should have a hydrolysis problem and so forth. So I would highly recommend that you think about where you're at as you're doing these. And that oftentimes can help you sort of focus on how to do the calculation. Any questions on that there? It may not. It definitely will not. And that's again why when you look at your ice table, you should understand what you're looking at in terms of the numbers. And that's why I put on there like, okay, I'm starting with this, I'm adding this. So you know that whatever you're adding in terms of moles, if you look at your ice table, if it's less than the moles you started with, then you're before. If they're equal, you're at the equivalence point. If whatever you're adding is more than what you're starting with, then it is past the equivalence point. So sometimes people also overlook sort of the numbers you see in the ice table because it does give you a lot of information about what is going on. Questions on that there? Yeah. It will always give you a buffer before the equivalence point. No matter what you do, you'll have some type of buffer. Not a great buffer in some points, especially as you get closer to the equivalence point. It's going to be a very bad buffer. It's not going to hold up very long, but you definitely will create in this sort of second region here, especially this kind of flatter region, before you kind of get to the rise, you definitely will create a buffer. And even all the way to the equivalence point, technically, you'll have a really crappy buffer, but you'll have some type of buffer sort of happening and stuff like that, yeah. And that's why, again, pretty much Ka problem on this one, buffer, hydrolysis, strong base, Again, those 4 distinct parts and understanding where you're at, extremely important in these type of calculations. Question on that. All right, we're going to lay it up there. We'll do an example of this next time, and we'll